In this video, we look at two examples, choosing a sample size when estimating a proportion and calculating a hypothesis test for one proportion. Example 1, we look at how to choose the sample size. When collecting data, we choose a sample size suitable for the purpose of the study. Oftentimes, this means choosing a sample size large enough that the margin of error is sufficiently small that the sample is useful. The LMC-associated students are conducting a survey to determine what proportion of students support an increase in fees to pay for a health center on campus. How big of a sample is required to ensure that the margin of error is smaller than 0.04 using a 90% confidence interval? So in this research design, we know that we want our margin of error within 4% or 0.04, and we know we want to be 90% confident. So we know from chapter 5 that the margin of error for sample proportion is calculated by taking the z-score and multiplying it by the standard error for a proportion. That's the square root of the proportion times 1 minus the proportion, all divided by the sample size. So our goal is to use this formula and find the smallest sample size n so that this margin of error is smaller than 0.04. So for a 90% confidence interval, we're going to use the critical value, the z star, or just the z value, if you want to call it that corresponds with 90% confidence. So that's 1.645. So our calculation here is going to be 1.645 because we're 90% confident, multiplied by the standard error formula, and we want all of this to be less than 0.04. So now this is a little tricky because we don't know the sample size, but we also don't know the proportion. We haven't gone out and conducted our study yet. So we use the proportion value that's going to give us the largest margin of error. So the sample size n, that's the value that we want to solve for. Since we don't have an estimate of the population proportion p, we are going to use the worst case value. So it turns out that the margin of error is largest when p equals 0.5. So we typically use this value to calculate the sample size n. So I've started off our calculation by putting in 0.5 for the proportion. So we're always going to use that when we're trying to calculate the sample size because it's the worst case scenario. And then we're just going to work backwards through this inequality to solve for n. So remember, an inequality works similar to having an equation with an equal sign. If we have any negatives that we multiply or divide by, that's when we change the direction of the inequality. In this question, we don't have any negatives, so we're going to have our inequality stay in the less than inequality throughout the whole calculation. So the first move I did is on the top of the calculation inside the square root, I multiplied 0.5 times 0.5 to get 0.25. So the second row shows my simplification of 1.645 times the square root of 0.25 over n, and that's all going to be less than 0.04, which is our margin of error. So now I'm going to move that 1.645 over to the other side of the inequality. So just like an equation, we can divide both sides through by 1.645. So in the next row, we see we've got the square root of 0.25 over n less than 0.04 divided by 1.645. So I do that division over on the right side of my inequality, and I get the square root of 0.25 over n is less than 0.0243. So the 0.0243 came from dividing the 0.04 by the 1.645. Now I want to undo that square root. So I put a note over here. I'm going to square both sides of my equation to undo the square root. So in the next line, you can see I've got my square root and then it's getting squared. Those are opposite operations, so they're going to undo each other. And then on the right side, we are squaring the 0.0243. And I rounded that 0.0243 to 4 decimal places. If you want to carry it out to more decimal places, that's more accurate, that's just fine. So then on the left side, my square root and my squaring have undone each other, and I have 0.25 over n, and that's all less than 0.00059. When I squared 0.0243, that was a value less than 1, so multiplying something less than 1 by itself gives us a value that's even smaller. So we get a smaller value, less than 1. Now I want to move that n over to the other side, and again, we're assuming everything's positive values here. We're not going to have a negative for our sample size, so we don't have to worry about changing direction of our inequality. So on the next line, we've got 0.25 less than 0.00059n. And then our very last move is to divide by the 0.00059 on the other side of the inequality. Notice now the greater than sign is towards the end, so we can rearrange that. So after we do the division, we get 423.7288 is less than n. Usually when we write inequalities, we write it with the variable first. So if we flip that around, we have n is greater than 423.7288. If you want to just round up to the whole number that's nearest, we could say n is greater than or equal to 424 for our sample size. So you would want a sample size of at least 424, and you could go larger than that, and your margin of error would be 4%, 0.04 or smaller. In example 2, we are going to calculate a hypothesis test for one proportion. After calculating the minimum sample size needed, the LMC associated students conducted a survey to determine what proportion of students support an increase in fees to pay for a health center on campus. Out of 430 LMC students surveyed, so their sample size was bigger than 424, so they used the calculation we just did to make sure they got 424 more students in their survey. Out of the 430 LMC students surveyed, 226 support an increase in fees to pay for a health center on campus. Is there evidence that more than half of LMC students would support an increase in fees to pay for a health center on campus? So first step is to set up our hypotheses. So we first want to identify what our proportion value is. We're using proportions because this is categorical data. So P is a proportion of LMC students who would support an increase in fees. If you imagine students asking the survey, they might say, do you support an increase in fees to pay for a health center on campus? And the responses would be yes or no's. So they would count the students who say yes, they support the increase in fees in their surveys. So our null hypothesis has to have equality. Since they're looking for more than half of students to support, we're going to use 0.5 or 0.50 for the value we compare our proportion to. Our null hypothesis is going to be the proportion equals 0.5, and our alternative hypothesis is going to say the proportion is greater than 0.5. That greater than inequality in the alternative hypothesis is because this question that we've highlighted is asking for evidence that more than half of the LMC students support an increase. So that's why we're using the greater than inequality in our alternative hypothesis. Recall that the null hypothesis and the alternative hypothesis are always competing claims. They can't both be true. So we set that up correctly here. You would either have equality or the alternative choice is a greater than, but those both would not be true. So step 2 is to collect the data. So we're going to write down the sample proportion, the sample size, and then calculate the standard error. So the sample proportion is the data from those students who were surveyed and said that they would support, yes, they would support increasing student fees for a health center. So that was 226 out of the 430 students surveyed. I like to convert to decimal, so rounded to 4 places, that would be 0.5256. Our sample size, N, is 430 students surveyed. So now we're asked to calculate this standard error. So we could do the estimated standard error and use the p-hat value, but since we're using 0.5 in our hypothesis test, we like to use that value in the standard error. When we head into StatCrunch, you'll see StatCrunch uses the value from your hypothesis test setup to calculate the standard error. So our standard error calculation here is the square root of 0.5 times 1 minus 0.5, all divided by 430. And so when we check that on our calculators, rounded to 4 places, we get 0.0241. Now we need to record the z-score and the p-value, and then we want to compare that to our significance level. No significance level was given in our question, so we are going to use 0.05 by default, that 5% significance level. Let's head into StatCrunch. So this is proportion stats. We're working with just one sample, and we already have all the sample values, so we're going to do this with summary. So here in StatCrunch, We don't need a data file since we have the summary information. So you can just go ahead and open a new StatCrunch window here. And then I'm going to go to Stat, Proportion Stats, one sample with summary. Here we are. Our successes were 226, and that's just the number of people who said yes, they would support an increase. What we call a success in statistic is just what we're counting. I sometimes imagine sorting through piles of paper, and if it's what you're looking for to count in your numerator, you put that over in a pile by the side. So you'd say, oh, that's what I'm looking for. That's a success. But there's nothing good or bad about these counts. And then our number of observations, that's our sample size, our total survey. Now notice by default, the value in the one sample proportion hypothesis test is 50% or 0.5. So in this case, since we're checking for a majority of students, more than half, we don't have to change our 0.5 value. In our alternative hypothesis, we do want to pick the correct inequality. So we're going to choose the greater than inequality. And then I like to see the p-value plot. So I'm going to scroll down and check p-value plot and click compute. So you can see here's our count, 226, and our total 430. Our sample proportion is an exact match for the calculation we did by hand. StatCrunch goes out to 7 decimal places, so it's always more accurate than what we do in our calculator and round. And then the standard error, you can see that's a match also for our calculation, 0.0241 we got when we rounded. And then the z-stat and the p-value are found using the normal distribution. So we can arrow over to see that standard normal distribution graph. So they use the z formula to get the z-stat. And so we see on that graph that's a little more than one standard error above the mean. And our p-value that corresponds with that we find using the normal distribution area that we definitely want to outsource to a computer. We don't want to try to do any area calculations by hand for a curve. Gives us 0.1444. So that's above our significance level, 0.05. So that's going to help us write our conclusion. All right, so here in step 3, I've recorded my values from StatCrunch, my z-stat, my p-value, and then I put a note that my p-value is above 0.05. So now it's time to write our conclusion. So since the p-value is above alpha equals 0.05 significance level, we fail to reject the null hypothesis. A more detailed way to say this is to say that there is not enough evidence to conclude that more than 0.5 or 50% of LMC students would support an increase in fees to pay for a health center on campus. So this is a case where we did a study, we ran our hypothesis test, and we did not have enough evidence to conclude what the alternative hypothesis is saying. Our p-value is above the significance level. Okay, we'll look at some more examples working with proportions in the following videos.